you and I get to take a look at the concept of a hypervisor and how they operate to create virtual environments for other guest operating systems to go ahead and run. Let's begin. I'd like you to imagine that it's 20 or 30 years in the future and you and I are going to a movie. However, movies of the future are not like the movies of today where we sit in a chair and we watch a film. In the future, we get a full bodysuit and they hook us up into this apparatus, and as part of the movie, they feed all 5 of our senses: our touch, our sight, our taste, our smell, and our hearing. And here's my question. If we were in these suits and having all of our senses fed, is it possible that we might not realize that we're in a movie and we might think that's part of real life? Now, we can apply that analogy of the movie theater of the future. We can apply that to the world of virtual machines and virtual environments today. For example, if we take a physical computer like a Windows computer and we power it up, it's going to do several things. There's going to be electricity that's sent to the motherboard. It's going to take a look at the read-only memory and the BIOS, the basic input-output system for that device. It's going to do a power-on self-test. It's going to read information from the complementary metal oxide semiconductors. It's going to boot to the hard drive. There's going to be a hardware configuration that somewhere looked at to identify all of the hardware and associated peripherals that are attached to this machine. It's going to load drivers, and that includes device drivers and system drivers. And eventually, when it's done, it'll create a user interface for a human to interact with it, whether it's a command line interface or a graphical user interface. Now, as part of this Windows machine booting up, it made a list as it booted up of the things that were attached to it. For example, is there a keyboard? Is there a mouse? Is there a monitor? Information about the drives. USB port information. The memory that's available to the system. The PC knows about all of those. And then with the appropriate drivers, it's taking advantage of those resources. Now, when we compare that to a virtual machine, when a virtual machine boots up, for example, it also could be Windows. However, we don't really have the keyboard, mouse, monitor, drive, USB, and memory that are dedicated to that device. Instead, in a virtual environment, we can create a list of the elements that we want to make that operating system believe is available to it. For example, the keyboard, the mouse, the drives involved, USB ports, the memory, and adding onto that the type of CPU that's involved. And so as a virtual machine boots up, it believes it has this nice laundry list of features that it can use. But instead of having the physical resources like the real PC does, all of these resources here are virtualized. Or if you want to think about it another way, we can say those are lied about. And that, my friend, brings up the next logical question. What type of a system or software would have the ability to go ahead and lie about all of these resources to an operating system so it believed that they were actually right there? And the answer to that question is called a hypervisor. A hypervisor is some type of a system, normally in software, that emulates these resources so that other operating systems like Windows or Linux can actually boot up and believe that they have those resources available to them. I mean, from the operating system's perspective, it looks and feels like a keyboard. It looks and feels like this type of processor. So the purpose and function of a hypervisor is to create an environment for an operating system to run where that operating system believes it's the real deal. Now, regarding the types of hypervisors, there's basically 2. We have a Type 1 and a Type 2. And again, whenever we think hypervisor, think of the entity or software that's creating that virtual environment for some other operating system to run in. And let's start with a Type 1. Now, we have to have some hardware somewhere that's actually providing the functionality. So we're going to call this box host number 1, the physical box that's going to be running our hypervisor. And a Type 1 hypervisor, also called a bare metal hypervisor. On our hardware, we'd have the hypervisor running directly on that hardware. And then on top of that, we could have our virtual machines. For example, maybe we have a Windows virtual machine running as a VM. Maybe we have a Linux running as a VM. And the fun part is that the Windows machine believes that it's running on a real dedicated PC, when in reality, the virtual environment that Windows is running on this host, that VM is all virtualized. So this is an example of a Type 1 hypervisor, where we have physical hardware, the hypervisor runs directly on that hardware, and creates the virtual environments for these guests. A Type 2 hypervisor does not run directly on the hardware, and we have some type of a host operating system. For example, that host operating system could be Windows or Linux. That's running and installed on that computer just as if it was a normal computer. But then on top of that, we'd run a separate application, and that separate application would be our hypervisor. So then within this hypervisor, we can create our virtual machines for Windows and our virtual machine for Linux, or a virtual machine for iOS. which could include the iOS from Apple or it could include the iOS from Cisco, depending on what type of environment that we're emulating. And because this hypervisor is simply just an application that's running, this same computer, which we'll call host 2, could also run other native applications. Now, regarding an example of a Type 1 hypervisor that runs directly on the hardware, a great example of that would be VMware's ESXi. And an example of a Type 2 hypervisor, where we have a host operating system in place, like Windows or Linux or Mac OS, and then we run the hypervisor as an application. Examples of that would include VMware Workstation. If someone walked up to us and said, hey, can you tell me the benefits of virtualization? There's a huge laundry list, and in this nugget we're going to cover a few of those, as well as discuss some of the virtual networking components. So let's consider this topology. Here in this demilitarized zone, we have a couple of servers. We'll have server A and server B. And if both these servers have the same exact content on them, and maybe we have a load balancer with the intent of sending some sessions to server B and some client sessions over to server A, we can still have a situation where server A is at 20% utilization and server B is at 30% utilization. And what's the problem with that? Well, you may say, Keith, there's no problem. They're both underutilized. So what's the problem with that? Well, on server A, we have 80% capacity that's going unused. And on server B, at this moment in time, we have 70% of utilization or resources that are unused. And the bummer is, we have to pay for all that. So we had the two physical servers, and we're paying for electricity for them and everything else. But if they're underutilized, we're basically wasting some of those resources. However, if we had a hypervisor running on some hardware, and then we spun up server A as a virtual machine and server B as a virtual machine, and let's imagine that server A, the virtual machine there, is taking up 20%, and virtual machine B, server B, is taking up 30%, we still have that remaining 50% regarding all the resources on this hypervisor and on this host that we can still use to bring up other virtual machines and other virtual services. So we can get greater utilization of our equipment. Also, it's very, very easy to spin up a new server in just minutes compared to putting up a new physical server, which would have to be racked and stacked, and then have the software installed. And if that's a manual process, that could take hours or even days. And if these two servers are virtualized servers, we could also leverage virtual networking equipment. So we could have them both connected over to a virtual switch that exists logically in the hypervisor. And then we could establish connectivity from those VMs as well out to the physical world through the physical network interface cards on the hypervisor itself. So for many of the elements in our networks, it does make sense to virtualize, including doing virtualization for our servers, virtualization for the networks and routers and switches and firewalls that are connecting those servers and devices together, virtualizing desktop machines for our end users to connect and then work inside that virtual machine as they carry out their duties as an employee at the company. We can also virtualize our storage. And then behind the scenes, we have a host or a set of hosts running hypervisor software that's creating the virtual environment that's providing the infrastructure. So Microsoft has a hypervisor environment called Hyper-V. VMware has a hypervisor environment called ESXi. And other companies like Google and Amazon Web Services have their hypervisors as well. And in those hypervisor environments, we can create virtual machines, and those virtual machines could have virtual network interface cards. And those virtual network interface cards could connect to virtual switches. And those switches could lead to virtual routers and virtual firewalls. And the fact that it's all virtualized makes it that much easier to manage it all and configure it from a single pane of glass, or from a single console where we can access and reach everything. And for an example, from a Hyper-V perspective, we'd have our virtual machines. They would have a virtual network interface card that connects to a virtual switch. And then that virtual switch can be associated with physical network interface cards, which then go out to our physical networks. And if those physical switches on the outside and the routers connected there lead out to the internet or to our corporate network, then based on the controls and what we want to have happen, we can allow network traffic from a VM and its virtual network interface card to go through the virtual networking environment to reach both other virtual and physical networks. To help reinforce how quick and easy it can be to bring up a virtual machine, I'd like to walk through a demonstration lab with you of creating a virtual switch and a virtual machine in Hyper-V. If you'd like to join along, if you're logged on to cbtnuggets.com, there's a link associated with this nugget so you can practice the hands-on lab right alongside me. So here in this Windows server, we have opened up the Hyper-V Manager. And let's go ahead and click on the server name over here, which is dc-nug. And then over on the right, let's go ahead and select Virtual Switch Manager. So we're going to create a brand new virtual switch. For this demonstration, we'll create an external virtual switch. That's one that connects both to virtual machines and also has links to physical interfaces on the Hyper-V host itself that allows connectivity out to the physical networks. So with external selected, we'll click on Create Virtual Switch. We could give it a name, we could put our notes in, and if we wanted this to be associated with a specific VLAN ID, we could add that as well. I'm going to leave the defaults in place. We'll call our brand new switch New Virtual Switch, and we'll click on OK. So now we have this new virtual switch, and when we create VMs, we can connect them to this new virtual switch. So to create a new VM, for the benefit of connecting it to that switch, we can right-click over here on the server, DC-nug, hover over New from the dropdown, and select Virtual Machine. It walks us through a wizard to create a new virtual machine. We'll click on Next. We'll call this machine New Virtual Machine, and click on Next. We'll leave the default generation, click on Next. I'll leave the default memory, click on Next. And let's go ahead and connect this new virtual machine to that new virtual switch that we just created. So with that association between the virtual network interface card on the VM and this virtual switch in place, we'll click on Next. We'll leave the defaults in place regarding the new virtual hard disk, click on Next. And then let's specify that we want to install an operating system on this VM. So I'm going to click on the image file, .iso, and then click on Browse. And I have this teeny itty bitty ISO image. It's in the Downloads folder. So if we navigate to Downloads, is dsl.iso. So if we double click on DSL to select it, that'll give us the look and feel of a new VM being brought to life inside of Hyper-V. And then we'll click on Next, and then we'll click on Finish. So it's created all the individual components for that VM. And if we want to edit any of them, we could just right click on that new virtual machine right here. And from the drop down list, click on Settings. And here we could change the memory or processor or the controllers or the network adapter. So right here, if we expand the network adapter, it shows us that the network adapter is connected to the new virtual switch. So that all looks good. We'll click on OK. And if we wanted to start this new virtual machine, we simply right click on it and from the drop down, select Start. So now that new virtual machine is powering up, it's going to boot from that virtual ISO image that we associated with it. And if we right click on that virtual machine and click on Connect from the drop down, it'll bring us up a window for that virtual machine so we can watch it boot. And there it is, DSL for Darn Small Linux, or something very similar to Darn as the first letter there. So in this hands-on lab, we've demonstrated how easy it is to create a new virtual switch, a new virtual machine associated with that switch, leveraging the benefits of a hypervisor, such as Hyper-V. Whether we're using physical servers or we have hypervisors and creating virtual servers, there's a good chance that those servers are going to need access to data, and they need to get to that data without a lot of delay or latency. And so we have several options when it comes to network-based storage. And in this topology, this is representing a VMware vSphere environment. So we have 3 ESXi hosts, 1, 2, and 3. Each one of these hosts, which is running a hypervisor, is running multiple virtual machines and virtual servers. And when those virtual servers are reading from or writing to disk, they're relying on this ESXi host for those reads and writes to successfully happen to storage. Now, if each of these hosts has just local storage, that's okay until we have one of these servers fail, and then all the storage fails. And if we want to have one of the VMs that was running here now start running over here, if we're using local storage only, that's not going to work so well because that storage went away with that individual host. So by moving to some type of network-based storage, each of these hosts and their virtual servers can access this shared network-based storage. And if a single host fails, they're not taking the shared storage with them. The other hosts can still access that storage. And one common term that comes up is NAS, representing network attached storage. And with NAS, we usually have some kind of a dedicated single device with some hard disks in it. It'll have a minimal operating system that allows the basic input-output regarding the file system, and it has an Ethernet adapter that connects it to an Ethernet network. And then maybe on this file system, they're using NFS as a protocol to allow devices to write to and read from this network-based storage. And relatively speaking, getting a NAS on the network is not very expensive. But in larger environments where we need even more storage and higher reliability and higher speed to that storage, we may opt for another type of network storage, and that is SAN. And with SAN, a storage area network, think of it like a special dedicated network with multiple storage devices all working cooperatively to provide the network storage. And there are some very creative solutions for SAN as well. In the case of VMware, they can do this with their vSAN solution. They can take multiple ESXi hosts, multiple hypervisors, with their local storage, And they can take that local storage and they can logically make that available as one giant unit across the network. That would be one example of a storage area network, a SAN. And in this scenario, the storage area network is leveraging typical Ethernet to communicate back and forth, to share those local drives, and make all those individual resources appear as one larger unit. Another difference between NAS and SAN is that with NAS, it's usually file-based. So as we read to and write from the NAS server, we're reading to and writing from files. And with storage area network, we're typically using blocks of data as opposed to individual files. And when it comes to the higher end storage area networks, we also have some additional interfaces and methods for accessing that data. One option is fiber channel, which has a special purpose storage area network fiber channel network with interfaces to that network that the servers can go ahead and use to access the data. Or if we want to leverage traditional Ethernet, we can use fiber channel over Ethernet. Another SAN technology that can be used is iSCSI. Now, SCSI is a small computer system interface that was originally created to be used with an adapter that went to a local hard drive using SCSI commands. And with iSCSI, we're using those same types of SCSI commands, but doing it over an IP network, hence the term iSCSI. Another high-speed and low-latency technology used to access storage area networks is InfiniBand. And there's many factors that go into the decision regarding which type of network-based storage we're going to use, including the cost, and the amount of storage we need, and the type of systems and servers that are going to be accessing that storage. Now, in the event that we're using Ethernet as the communication path between our servers and hosts and the network-based storage and the storage appliances, one of the challenges is that if we're moving a large amount of data, at layer 2, the MTU, the frame size for Ethernet, is around 1500 bytes in length. And that means if we have a large file that we're sending to storage or retrieving from storage, that is going to be chopped up into many, many frames, which will be encapsulated in many, many packets, and each of those frames and packets are going to have overhead. One of the techniques is, why don't we just change the rules? And I can hear you now saying, what do you mean change the rules? Well, we can still use Ethernet, but what if we told all the devices, including our layer 2 switches, that we're going to change the MTU to be something much larger than 1500 bytes? For example, if we told our switches and everything else in the path that frames could be 9000 bytes, then if we're sending large amounts of data back and forth, they're being chopped up into fewer frames and respective packets, and that means there's less overhead. And if we have devices that are configured to support that, that is referred to as supporting jumbo frames. And so if we have a network environment that supports jumbo frames, we can more efficiently move large amounts of data because larger frames means fewer number of frames with less overhead associated as a result.
Thanks for watching our second and press the button below, like, subscribe, and bell icon.